Okay. So, where are you all? So, ma'am has covered till she has started. Ma'am has explained about how the procedure, how you have to define a procedure, right? After that, how to define a variable, and a few examples with respect to that. Based on that, if you are making a procedure call, what are the two different types of substitutions existing, models existing? In that, which are the which one is the one which Lisp is using? So, what are the two substitution models? Remember,
Normal order, applicative model.
normal order, applicative order, and Lisp uses which one does the Lisp uses? See,
Application.
yeah, applicative order. Lisp uses applicative order. So, what is the difference between these two? In applicative order, what happens first? It will solve the whatever expressions you are having, that will be solved, and then it will take. Then only the procedure call will be happening. Whereas in the normal order, it doesn't solve anything. That is like it doesn't apply, and it keeps calling the procedure as such. Whichever way the variable is getting the value, whether it is an expression or it is a value, it will be taken forward in the same way for the normal order. In applicative order, what it happens, it first solves it, and then only that particular value only will be applied, taken forward for the next level. So that is about the procedure. How do we take up with respect to the substitution model? So next we have discussed with respect to. So since you have learned with, how to write a procedure, so what are the different ways of defining? That is, usually when we can write a program in many ways. So when you write a program in one way, how it will be taken up? That is how we have seen with respect to linear recursion. So if you are that has been explained with respect to the example, factorial example. So usually when we take up the factorial example, we take up with respect to n into n factorial, right? Yeah. So n into n factorial is the one which will be taken up. So and here in this programming language, we don't have any explicit looping statement. So how do we make a looping statement? It is nothing but we have to call the procedure again and again. So it is recursive procedure call. Okay. So explicitly, we don't have any other looping statements. We whatever is the basic syntax, whatever is required, all those you have studied by this time. So how to define a procedure? If you have any conditions, you can use if it is a single if else partners, then you can go with if. You can mention the condition. Immediately, whatever comes, that will be considered to be as true expression. After that, whatever comes, that will be considered to be as false expression. Similarly, if you are having multiple conditions to be given, something like your switch case or else if ladder, then we can go with cont. So cont, first condition you can mention, second condition you can mention. So the syntax you have to follow. Okay, and the statement else you will be getting it only for the cont. There is no else written for the if part according to the syntax. Okay. So keeping that in mind, if you are taking up this factorial example, so how we can do it? So factorial is nothing but if you are having when your n reaches to 0 or n reaches to 1, we can stop it. So so if your n is equals to 1, then you are just returning the value 1. Otherwise, you are applying multiplication operation onto the n value. Next thing will be your next procedure call. So factorial of which one? It is n minus 1. So like that, it keeps doing till your n reaches to 1. So like this, if you're defining a procedure in this way, what happens? Your procedure call, say for example, with respect to factorial of 6, if you are writing it, your factorial, this is how the substitution will be happening. This is how you will be getting up the final answer. So now if you see the pattern here, or how many times the procedure has been called with respect to if you keep analyzing with respect to the space as well as the time consumption, how much it will be. If you are saying factorial of 6, we are calling the factorial procedure for 6 times. Along with that, what happens? You are even saving the contents. So if you see first time when you are calling, you are maintaining the information regarding multiplication operator and 6. So that has to be saved. Along with that, you have the content factorial of 5, the next procedure call. Similarly, when you're calling for the second time, what happens? We have to maintain the informations like multiplication of 6. Oh, yes, sir. Multiplication of 6, multiplication of 5, and then followed by factorial procedure is getting called. So that means whenever you are making the procedure call, you should take care of the contents, whatever you are having, that is the multiplication along with the content, right? So your the space requirement is also linearly how much space you need for storing all this information is also linearly getting expanded. So if you see by the time you reach to a procedure called factorial of 1, you had to maintain multiplication of 6, multiplication of 5 till multiplication of 2. So that means almost n minus 1 contents you are having for you had for maintaining, right? So this is what we call it to be as, this is the reason why we say for a linear recursive process, that is if you are writing a procedure in this way, that is for n into, that is multiplication of n with factorial of n minus 1. That means your factorial, the procedure, the same procedure is getting called at the later part. Then what happens? We call it to be as linear recursive process. The process what you're going to achieve is linear. And when you say linear recursive process, when with respect to time and space, when you talk about, that is the order of growth when you talk about, that is also linear. How many times we have called the procedure? Almost n times. And how many contents we had to maintain by the end of it, especially in the middle statement, if you see, you can analyze it. So you have almost n contents which you had to maintain. So we call, so we can consider that whenever you are writing a procedure in this pattern, that is in this fashion, then we call it to be as linear recursive process, and the order of growth will be for both space as well as the time. It will be theta of n. Okay. I think all these things ma'am has already covered, right?
Yes, ma'am.
Okay. So coming to the factorial same procedure, if you want to rewrite, you can even rewrite it in this way also. So then what happens is you will be getting at the process how you will be received. It will be the process will be mentioned in this. This is the pattern what you will be getting with respect to the linear iterative process. So then if you see the pattern here, we are calling the procedure again and again, but only the values are getting modified. So what will be the order of growth in terms of time, that is in terms of steps? How many times we are calling this factorial procedure? We had called the factorial procedure almost n plus 1 times. So plus 1 means it will be a constant. We don't give much importance for that constant values. So what will be the with respect to order of growth, with respect to time or steps, we can say it to be as theta of n. Okay. So process means and we are talking in terms of complexity. Similarly, when you consider this with respect to space, how much space it is going to occupy. Here, when you see the procedure is getting called and each values, the variables are getting modified. So only the same arguments values are only had to be maintained. We don't have any extra contents which we had to maintain like the previous one. So what we can say it to be, we can consider it to be as the constant one. That is like always whenever you are calling this procedure factor ITR, we have only 3 contents. So every time you call, this is only 3. So that means whenever you say it is a 3, 3 is considered to be as a constant. So we can say that theta of 1. So order of growth in terms of space, we can consider it to be as theta of 1. So the same procedure, say now regarding block structure, you have discussed with respect to in the square root procedure, right? In square root procedure, we have seen like if you're say in this procedure itself, if you see, we have factorial function written in 2 procedures. That is, factorial is one procedure, and we have fact ITR to be as another procedure. So now, if you want to make it to be as a block structure, what is the importance of this block structure? Is this also covered by ma'am? I didn't. Ekant, you were telling something?
No, ma'am.
This is covered by ma'am?
No, ma'am.
Okay. Previous one was covered. Linear iterative process.
Ma'am, the block structure was not covered. Like what that meant. Otherwise, everything was covered.
Okay. In square root procedure also it was not covered?
Newton's method, no, ma'am.
Yeah, in Newton's method.
Ma'am explained that problem, ma'am, but like what is that block structure was not told.
Okay. Okay. So block structure is nothing but if you want to focus, I mean, like if you want any particular function to be dedicatedly used only for that particular purpose, then we can make it to be as a block. So for example, like if you see here in this, we have two procedures. So one is the factorial one, and the other one is fact ITR. So when we are having these two procedures, and fact procedure is being closed, and then only we are defining the fact ITR procedure. So that means what? If anyone wants, we can access fact ITR also. If anyone wants, they can access fact ITR through fact, or directly fact ITR can be accessed. So that means it is open. If you want to specify, that is, if you want to mention that it has to be specifically this fact ITR should be used only by only from this factorial procedure, then what we have to do is we have to block it. So how we can block it? So how we can block is instead of writing this procedure here, that is like you start the definition, define factorial, that is factorial procedure, fact n. After that, you can define the same procedure. You can define this entire part. Define fact ITR can be done inside the factorial procedure. And then what you can do is you have to call your fact ITR 1, 1 and n. 1, 1 and n you can put over here, and then you can close your fact procedure. So that means you are making your fact ITR procedure dedicatedly for only for this factorial procedure. No one else can access this fact ITR from outside. So this is what we call it to be as the block structure. So you are making it to be as a block. So that block can be used only within that. It's like a local variable. So if you have your local variable concepts, what you will be doing, the variable whatever you are declaring within that block in the sense within that curly braces, that variable can be used only from there. It cannot be used outside. So same concept here. Now what you are doing is you are defining a procedure. That procedure is defined inside another procedure. So you in this particular language, what is the beauty is you can define a procedure inside another procedure. So when you start defining fact procedure with n, before closing the fact procedure, you have defined fact ITR procedure, you close that fact ITR procedure, only then you can define what the body of your factorial procedure. So as the body of the factorial procedure, it says fact, you're calling the fact ITR procedure 1, 1 and n. And you are closing the factorial procedure. So when it comes for the execution, what happens? First time when you call fact 5, you will be calling. So where the control goes? Control doesn't come to the definition. When the control will come to the definition, for that you have to call that procedure. So it will be coming to this fact ITR 1, 1, where the value for n is 5. So it will become 5. And you will be calling this fact ITR procedure. So the point here is fact ITR procedure can be called only by this factorial procedure. No one else can call this fact ITR procedure. So this is what is called to be as block structure. Okay, so you're blocking your fact ITR specifically for factorial procedure. Only this one can use it. No one else can use it. Okay. So other thing is, one procedure can be defined inside another procedure. That is one new thing which you have to always remember. So what is the advantage of going with this block structure? What is the need for it? If you see here, from your fact n procedure, you are calling your fact n. So say you are having your fact, say your n is 3. Fact 3 you are calling. So what happens? Fact ITR 1, 1 and 3 it will be. So next time when you are calling, what happens? You will be doing your counter will become 1 into 1. So it will remain 1 itself. But your maximum will become 2. That is 1 plus 1. It will become 2. Max count will become what? It will remain the same n itself. And once again, you are calling your fact ITR with 1, 2 and 3. So what happens? You will be first checking whether you have reached the counter value or not. If not, again you are calling your fact ITR procedure, where now you will be doing 1 into 2, so which is 2. Your counter will be set to be as 2. Product will be set to be as 2, and counter will be set to be as 2 plus 1, 3, and max count will be set to be as that same value 3. Once again, when the procedure call is done, it will become like 3 is greater than 3. Condition won't be true, so it will come here. Again, you are calling fact ITR procedure, where you will be having 2 into 3, 6, and 3 plus 1, 4. So 2 into 3, 6. 6 will be set to be as the product value. 3 plus 1, 4. 4 will be set to be as your counter value. Max counting will remain it to be as 3 itself. So now you will be checking whether 3 is greater than counter. So counter is nothing but which is now 4. 4 is greater than 3. Condition is true, so it will return the product value, right? So now when you are calling this procedure, if you see this fact procedure getting called, I will just write only the p value, counter value and max value. So your p value, counter value and max value. So first time when you are calling, it was 1, 1 and 3. Second time when you called, it was 1, 2 and 3. Third time when you called, it was 1 into 2. So 2, 3 and 3. Next time when you called, it was 2 into 3, 6. Then here 4. Then here 3. If you see here this pattern, these values are getting changed. This is also getting changed. But what about maximum value? Maximum value remained same. So if a variable's value is remaining same, do you want that particular value to be passed as such? Because we are having the same value maintained, right? So when you make a procedure to be as a block structure, what is the advantage is you can make some variables to be as some variables, that is like you can say that this max count you can have in your fact ITR only two variables, and this n value anyways you have defined it in factorial n. So since this fact ITR is inside this factorial procedure, what happens? You can use that n variable inside this fact ITR. This is what we call it to be as the lexical scoping. I think this also might be covered in that Newton's method square root procedure. Was that done? Lexical scope, lexical scoping.
No, ma'am. We did it in compiler design.
Okay. Um, so here, when we are saying it to be as the lexical scoper, what happens is, what we are saying is, whether you want all the variables. That means if you want the number of variables, if you can reduce the number of variables, when you are calling your procedure, the number of values what you are supposed to pass, that can be reduced. So how we can reduce it? For that, if you make this definition inside the procedure factorial itself, then you can make it to be as a block structure. That is what we had done. That means this statement will come outside, and closing also will be done here outside this. Okay. So now what you are having is factorial procedure. Inside factorial procedure, you are having fact ITR. So in factorial procedure, we have one argument, which is considered to be as n. In fact, ITR procedure, we are having three arguments. One is considered to be as product, the other one to be as counter, other one to be as max counter. Max counter is used just for identifying whether the counter has crossed the limit or not, whether we can stop it or not. So for that purpose only, you are just maintaining the max count. So as I have said, if you are considering your n value to be 3, I have just listed previously, I have just listed only for the arguments, that is product, counter, and max counter. So when your n is 3, how the procedure calls would have happened? First time when you are calling, your product was 1, counter was 1, and n was set, n maximum count was set to be as 3. Second time when you are calling your fact ITR procedure, we had done this multiplication. So it is 1 into 1, so 1. 1 plus 1, which is 2, maximum count value, which is 3. Next time when you are calling your fact ITR procedure, 1 into 2, which is 2, 2 plus 1, which will be 3. This max count, we are not modifying anything. Next time when you do, it is 2 into 3, 6, 3 plus 1, which will be 4. This max count remains same. So if you see here, in this pattern, when you see, the product value is getting modified. Each time you are calling the fact ITR procedure, the value, there is a change in your product variable or product argument. When you see your counterpart, the argument, counter argument, when you see the value assigned, each time you call your fact ITR procedure, each time the count value is also getting changed. Now, if you see for the max count value, each time you call your procedure, this value remains same, right? So whenever, each time you are calling the procedure, still the value, the variable's value remains same. So is there any point whether we can reduce the number of arguments in this? Yes, we can do it. But when you are doing it, you have to make sure that your procedure is in the block structure format. That means your fact ITR is defined inside factorial procedure. So now what you can do? You can avoid using this max count procedure. And what you can do? You can have, you can directly use, wherever you had your max count, instead you can directly use the variable n. Wherever you had, that means here, when I'm saying you don't have to have this max count, that means fact ITR will have only two arguments, which is product and counter. We will not have the third argument because There is no point of having the third argument because the value remains same. Which value it was? It was nothing but it was the n value. So since you have defined fact ITR inside the factorial procedure, you can directly use this variable n itself, right? So wherever you had this max count mentioned, instead of that, what you can do is you can modify it with n itself. And when you're calling in the else part, when you're calling your fact ITR, we will not have this max count. This argument itself will not be there. So here also this argument will not be there. So what is the advantage? You can reduce your procedure call with one argument. So even though we say it is a constant value, but still that constant makes some change. So that is the advantage of making your procedure to be as a block structure. And this concept is what we call it to be as the lexical scoping. Is it clear? Have you understood? Do you want to write the procedure after making it to be as a block structure and with lexical scoping? Somebody?
Understood, ma'am.
Okay. So can you try out with this question?
Ma'am, we did this in the last class, ma'am.
Fine. Okay. So let's move on with the next process, which we call it to be as the tree recursion. So what? So for this, before we'll see how this why we are calling it to be as the tree recursion. So if we take up the example for Fibonacci procedure, see the Fibonacci procedure, it will be mentioned like this, right? So Fibonacci series means which will be all of us know. So 0, 1. So next numbers onwards, it will be 0 plus 1, 1, 1 plus 1, 2, 1 plus 2, 3. So it goes on like that. So if you have to generate this Fibonacci number, how the procedure will be written? It will be considered to be as if your Fibonacci number, if your n is 0, you can just return 0. If your n is 1, if your n value is 1, then you can return the same 1 itself. If your n is not 0 or 1, if it is any other number, how we can get it? We have to add the previous and the previous to previous number. So how do we get the previous and previous to previous? So it will be like fib of n minus 1 plus fib of n minus 2. So just previous value we can get it by using n minus 1. Previous to previous value we can get it by using n minus 2. So these two contents, whatever if you add, you will be getting the value. So keeping this, if you write the procedure, how do we write the procedure? So already I have mentioned the procedure here. So define fib of n. So we have only one single argument. So it is mentioned to be as n. And how many conditions do we have here? If you see here, we have 3 conditions. So we can't go with if statement because by using this if statement, it will give us only true or false part. So what we have to use? We have to go with cont. So when you go with cont, how it will be written? It will be written to be as cont. You can open the parenthesis. If your n is equals to 0, return 0. If your n is equals to 1, return 1. Otherwise, there is else part. We have to add. So plus fib of n minus 1, fib of n minus 2. And then close all the opened parentheses. So now if you see here, in this particular structure for this procedure, In the else part, we are calling the same procedure Fibonacci twice. So when we are calling the Fibonacci procedure twice, with respect to this example, if you take up fib of 5, if you take, it will be like first time your n value is not 0, n value is not 1. So it will be considered to be as we will reach to the else part. So there we are calling fib of 4, that is n minus 1, 5 minus 1, which is 4. Next you will be calling 5 minus 2, which is 3. Now the execution will be happening always the left to right, the execution will be happening. So first you will be executing fib of 4. So fib of 4, which is not 0 or 1. So again it will reach to the else part. Again you will be having fib of 4 minus 1, which is 3. And fib of 4 minus 2, which is 2. Again the execution will happen from left to right. So first you will be executing fib of 3. So fib of 3 will be further expanded. It's not 0 or 1. It reaches to the else part. So fib of 2 and fib of 1 will be called. Called in the sense it will be like this will be generated. Next the execution will happen from left to right. So fib of 2 will be executed. So fib of 2 again you are expanding. So fib of 2 minus 1, so which is 1. Fib of 2 minus 2, which is 0. So when your n value reach to 1, we are just returning the value 1. If your n reaches to 0, it is if your n is 0, it is returning 0. So like this, the execution goes on. So left to right, the execution happens. So if you see the arrow marks mentioned, so it will be like, if you see the arrow marks, it is clearly mentioned. So fib of 5, then fib of 4 will be executed, then fib of 3 will be executed, fib of 2 will be done, then fib of 1. After that, the control goes to fib of 0, and then control goes to fib of 1, and it comes to fib of 2, then again 1, 0. Again it comes here, it calculates fib of 3, then again it moves towards the left hand direction, then reaches at the end, only you will be getting the value. So if you see the arrow path, it is clearly mentioned like how the function calls work out. So evaluation will happen from left to right. Okay, but the problem with this is the tree recursion. For these type of problems, you can go for tree recursion. So, but the problem is, if you see here, uh, fib of 2, if you take up fib of 2, this procedure itself, this has been repeated here, this has been repeated here twice, right? The same operation has been done 3 times. So, this could be optimized. Okay. So there are certain improvements which we have to apply on this, but this is there are some procedures which can be done only in this way. But there are few disadvantages because of this. So that is like see, for example, fib of 2 itself, if you take up these many times, the same same computation has been done repeatedly, even though it has been calculated here again and again, it has been done. Similarly, fib 3, if you take, twice it has been done. So like that it is. So when you take up with respect to the structure, certain procedures, when you are writing, certain procedures can be written in this pattern itself. Okay, even though the complexity is little high. So now if you just discuss with respect to order of growth. So what is this order of growth? Order of growth is nothing but we are just calculating, we are just analyzing our procedure in terms of steps as well as in terms of space. So when you start analyzing it with respect to steps and space, for these type of procedures, which generates the process, that is tree recursion. So it's like a tree structure. So we call it to be as this generates tree recursive process. Why tree? Because it's in the tree structure. Recursive process because you are calling the same procedure again and again. So we call this to be as tree recursive process. Okay, so what will be the complexity? The complexity in terms of space, first let us see in terms of space. How the space has been occupied. So if you see the procedure calls, this arrow itself, how the arrows are moving. Arrows are moving, that is from left it will be executed, then it will move towards the right, and then it will be executed, right? So each time you are calling the same procedure. First time it is fib of 5, next it is fib of 4, next it is fib of 3, next it is fib of 2, next 1. Then it is done, it returns the value. So again, instead of fib of 1, it will become fib of 0. This is also done, it returns. So fib of 2 will calculate plus. So that value will be returned. So that is also done. Then again here it will be fib of 1. So again it is returning. So this is done. So this left hand side is done. You will be moving towards the right hand side. Again you reach to fib of 1, it returns the value. So that means whenever you're calling your fib procedure, maximum length, where what is the depth of your tree here? Only that much is the space which you are going to occupy, right? Once you reach to the leaf node, your procedure is returning a value, so it goes back. So that space occupied is left out. The stack is free now, right? So what is the space required here? If you are saying fib of, if you are saying n value to be 5, if you calculate the depth of this tree, how the depth is, how many rows you are, how many depth it is. So first one, second, third, then fourth. So the root node we are having it to be as 5. So I can say that it is the space requirement will be with respect to the depth. So I can say it to be as n itself, theta of n. So average case, so which is theta representation. So theta of n I can say, right? So with respect to space for Fibonacci procedure, the order of growth in terms of space, it will be theta of n. What about computation, the steps? So when we take up with respect to steps, so how many steps do we require for computing it? So if you see here, fib of 5, then 4, then in each step we are doing the computation. In each, even though if you say, for example, this fib 2 itself, that fib 2 itself is getting repeatedly done. Or if you take fib 1 itself, we are repeatedly doing the same process, right? So that means the process, the computation time required for doing for these type of procedures, it is more than n times. So if you see 5, then 4, then 3, then 2, 1, 4, 0, then you are doing the calculation, it comes, then again you are returning, again you are calculating again. So how so it is like it is in terms of n, when you are saying, I can't say that it is equal to n. I can't say it is less than n. I can't say it is always more than n. So when I say more than n in order of growth process in algorithmic way, how I can represent it? I can say that it is exponential growth, right? So if it is say if it is almost n, I can say that theta of n. But in this case, the number of steps is not equal to n. Almost, that is like I can't say n plus 1 or n plus 5 and something like that. No, it is like for say if, here in this example I have shown with respect to fib of 5, right? Uh, if my procedure n value is 3, if my n value is 3 means only this is my portion, right? Only this is my calculation part. But as my n kept on increasing, the computation also kept on increasing drastically. It was not a small growth. It is very drastically, it kept increasing. So these type of growths we can represent it with respect to exponential. So I can say that it is exponential growth. So exponential growth, how we can represent some constant. So theta of some phi per n. I can say the order of growth for these type for Fibonacci procedure. it is having an exponential growth. So this 5, which stands for the golden ratio. So those, I think you have studied with respect to optimization, right? So you might be remembering this golden ratio. Okay. So here the point is, so you can write the procedure in any way. So when you're writing the procedure in any way, so either you will end up having linear recursive process, or you will end up having linear iterative process, or you will end up having pre-recursive process. These are the three process which you can achieve. So these are the three ways you can write the procedure. That is the point from this. So that is what has been tried to explain in this part, in this slide. So first we have written the procedure, and then we have seen how the each different phase you are writing the procedure. It will be increasing this how the process, what is your system requirement, how is it increasing. The same Fibonacci procedure, you can even write it in this way, like you are having defined fib of n, you are just defining another procedure, fib of fib itr 10n, where you are defined as another sub procedure, where you have mentioned it to be as a and b value. That is the initial values 1 and 0, and after that you have set your n value, whether you have reached the count or not. That is nothing but your n value. So from fib, whenever you are calling fib of 5, you are just calling fib sub procedure by passing the starting value 1 and 0 and the maximum count value. And here, what is the stopping condition? You can say that when your counter reaches 0, you can stop the content. You can stop your fib procedure. So how many conditions we have? Only one condition. So I can easily go with if statement. So if you are mentioning the condition, it is equals to count is equals to 0, you just return the b value. Otherwise, what you have to do, you have to calculate. You are calling your sub procedure, which is fib itr procedure, where your a will be nothing but a plus b. There is nothing but any, first time it will be 0 plus 1. So that. What about b? B will be nothing but your a value. That is, first what was your previous a? That will be your b value. You are just maintaining the previous content. Count, what you are doing, you are just reducing it. Each time you are calling your sub procedure, you are just reducing the count. So you can analyze this. You can just analyze this fib procedure. Say if you are having your n value to be 5. So fib of 5, when you are calling, first time it will be sub fib procedure, that is fib itr procedure, itr with the value 1, 0 and 5. I'm going out of the screen. Then you are checking the condition, and again you are calling the sub fib procedure, that is itr procedure, where a plus b, that is your a is nothing but the previous value, b is nothing but previous to previous value. So it will be 0 plus 1, which is 1. And which one we have to maintain? We just have to maintain the previous value. We don't want previous to previous. So your b will become a value. So it's nothing but a swapping concept. And the counter is getting reduced. Next, when you are calling, it will be, I'll just write this A, B and count value. So next time when you are calling, it will be 1 plus 1, which is 2, and you are swapping. So this value will be reaching to the next value, so which is 1. Counter will be reduced. Your count has not reached to 0. So again, you will call the procedures. Fib ITR will be called. So where 2 plus 1, which is 3, and this value will be swapped. So your B becomes your A value, so which will be 2. The counter will reduce, so which becomes 2. So again, 2 plus 3, 5, and this value will be taken, so which means your B becomes 3, and counter is again further reduced. Next, next time when you are calling, it will be 3 plus 5, which is 8, and this 5 value will be taken to be as your the B part, and the counter is reduced. So now your counter has reached to 0. So now what it is going to return? It is going to return your B value. So fib of somewhere I went wrong. Yeah, fib of 5 is 5 only, right? So 1, 2, 0, 1, 2, 3, 4, 5. Yeah, fib of 5 is 5. So it will just return the value 5. Fib of 6 is 8. Okay, so this is what type of process it is going to generate. By seeing this, what type of process it is generating for this Fibonacci procedure. Just by seeing the structure, we can make out, right? So again and again, we are just calling the procedure. Fib's ITR is getting called only by modifying the A, B, and count values. So what happens? We are just just by seeing this structure itself, it is understood that it is linear iterative process. So the procedure, whatever you have defined here, this is going to generate linear iterative process. So whenever we say it is linear iterative process, what is the count here? How in terms of order of growth, in terms of time, if you take out, that is in terms of steps, if you see, which will be nothing but when you say n is 5, so 1, 2, 3, 4, 5, 6, 7. So almost uh, 5 plus 2. So fib of 3 also it will be 2 extra part. So it will be almost constant pluses there. So I can say it to be as theta of n will be your order of growth in terms of time. How about the space? Is there any extra things which you have to say? No. Here only the argument values you have to say. So each time you are calling, the value argument value is getting modified. So is the argument size, the number of arguments which you are making, is it changing? No. So it always remained 3. Each time you call your sub procedure, each time it is 3 only you are calling it. 3 arguments are only passed. So we can say that order of growth in terms of space, it will be theta of 1 because it is a constant. Instead of saying theta of 3, which is a constant value, we can say it to be as theta of 1. So I'll stop with this. We'll continue with the next class.